All right. Today we'll look at the dimensionless parameters for a turbine. So as we have seen last time, some of the parameters are the same. So we have a head coefficient, which we are calling C subscript H. C for coefficient, H for head, which is GH by omega squared D squared. Now, in the case of the pump, omega was the angular speed of the pump impeller. Here it will be the rotor or runner of the turbine. And this is also called energy transfer coefficient because, as you have seen, GH is the energy transfer per unit mass for it. That is energy transfer between the rotor and the fluid. And then you also have a flow coefficient, C subscript Q, which is the flow rate. So here I have not put the superscript flow, Q by omega dq. It's also called capacity coefficient. And in the case of a turbine, the important output variable is the power that you extract from the fluid. So the power delivered by the turbine by rho omega cube d5 you can show is non-dimensional. And the efficiency of a turbine is the output by the input. So if H is the head that is available at the inlet of the turbine and P is the power developed by the turbine, then P by rho QGH. So this denominator here is the hydraulic power, okay, available. So this is defined in such a way that it is less or equal to 1. Usually it will be less than 1. In the case of the pump, it was a reciprocal of an expression of a similar kind. And omega here is 2 pi small n, where small n is the revolutions per second. So small n is capital N by 60, where 60 is the RPM or revolutions per minute. All right, now the efficiency we can write in this way. Instead of P, I can write Cp into rho omega cube d5. Instead of Q, I can write Cq into omega dq. And instead of H, GH, I can write CH into omega squared d squared. So this turns out to be the ratio of Cp to the product of Cq and Ch. Now, there will be 3 independent parameters, as in the case of a turbine, as in the case of a pump. But in the case of a pump, the important independent variable is Cq, the flow rate. Here, it's customary to use Cp. So we will express Ch as well as Cq as a function of Cp, Re, and the roughness ratio epsilon. Now, for high Re flows, which are turbulent and rough, the impeller surface is rough, the dependence on Re and epsilon can be neglected. Okay. So then there will be only one parameter, as in the case of one dimensionless parameter, as in the case of a pump. But here the parameter we use is Cp. So Ch will depend on Cp, Cq will depend on Cp, and hence eta will also depend on Cp only when the Reynolds number is large. Now, you would also like to have a specific speed for the turbine. It's also called a type number or shape number because the value of the specific speed at the maximum efficiency point depends on the shape of the turbine. So this is a non-dimensional parameter. So since it's called speed, we'll make it proportional to the angular speed. And we want it to be a number which is independent of the size so that it depends only on the shape. So we can have a family of geometrically similar turbines which have the same shape but different sizes. But for a given shape, the value of the specific speed at the best efficiency point will be a constant which is independent of d. As we have seen in the case of a turbine, Cp is an important parameter and Ch is also another important parameter. So we'll consider a combination of Cp and Ch, and combination of the dimensionless parameters are also non-dimensional. So let us look at a pi parameter, which is Cp raised to the power constant m, and CH raised to the power n. So we can write it as omega to the power minus 3m plus 2n multiplied by Py rho raised to the power m into GH raised to the power n, and then you will have d raised to the power 5m plus 2n. Now you want to choose m and n, these two exponents, such that this pi parameter is proportional to omega. So the exponent or power of omega should be 1, and we want that there should be no diameter in it, no length scale. So we want the power of d to be 0. So I have two equations, 5m plus 2n equal to 1, 0, and 3m plus 2n is minus 1. And this gives you the pi of this form, which will be given in all books, but the derivation will not be given. It is Cp raised to the power half divided by Ch raised to the power pi by 4. So this combination is proportional to omega. So it is omega to the power 1 times this quantity, and there is no diameter in it. So it is omega times square root of P upon rho divided by GH to the power 5 by 4. So this is the dimensionless, and we'll call it specific speed. We'll call it power specific speed of the turbine. In the case of a pump, and H was also there. So the specific speed of a turbine involves the important output variable, which is power. So we'll call it power specific speed. So we'll give it the same symbol, omega s. And as you can see then, since CH depends on Cp at large Reynolds number, you can say that omega s is you can, instead of taking Cp as the independent parameter, you can take the omega s as the independent parameter. And then you can say that the specific turbine efficiency is a function of the specific speed for a given shape when the Reynolds number is large. Now sometimes the value of specific speed may be quoted by a manufacturer who wants to sell a turbine. So what does it mean? Because omega s could be any value. Well, the value which they quote is the value of omega s when the turbine efficiency is maximum. So at the maximum point, there is a certain value of the power specific speed. And in the case of impulse turbines, this is roughly about 0.15. We have seen already in great detail an impulse turbine, a hydraulic impulse turbine, which is the Pelton turbine. You can have other kinds of turbines which are impulse turbines, but the fluid may not be water. Now we'll be looking at Francis turbines and Kaplan turbines. Kaplan turbines are axial flow turbines, and they have omega s about 2.5, and Francis turbines would have omega s about 1. So in the case of a particular application, if you have to decide whether you want to choose an impulse turbine or a Francis turbine or a Kaplan turbine, then you should look at the power that is required in the application. Okay, what is the speed of the turbine? That will depend on your generator, which will have a certain number of poles, and the line frequency will be 50 hertz. And you have to look at what is the head that is available. So power required and the head available will determine omega s. And if you find that this value is less than 0.3, then the best choice would be an impulse turbine. So if the fluid is water, then choose a Pelton turbine. If omega s lies between 0.3 and 2, you should choose a Francis turbine. That is a better choice. And if omega s happens to be greater than 2, then the best choice would be a Kaplan turbine. Now I've given you omega s in non-dimensional form, but if you look at the definition of omega s, there is a rho which will be constant for water. G is also a constant. So what engineers do is they define a dimensional power specific speed which does not have the rho and the omega in it. And instead of using omega in radians per second, they'll use it in RPM usually. So I've called it n tilde s, which is the rotational speed in RPM into power to the power half by h to the power 5 by 4. So this numerical value of this will depend on whether you're using metric units or English units. Whereas if you look at this quantity, the omega s, this is independent of the units that are used to measure P, H, omega, rho and G. Now similarity rules we have already seen in the case of pumps. We have an analogous relation for turbines. So if you have, say, two turbines, we'll call it turbine A and turbine B, which belong to the same geometric family. That is, the shape is the same, but the size is different, let us say. Okay. When they're operating at homologous points, which means that they're dynamically similar. So if they're geometrically similar, then geometric similarity is satisfied. And if the non-dimensional parameter Cp is the same for A and B, and the Reynolds number is high, then this is the only relevant parameter which controls dynamic similarity. So if these two are equal, then automatically Ch and Cq for the two turbines will be the same. So if we equate Cq, you see that the ratio of the two flow rates will be the ratio of the angular speeds into the cube of the ratio of the diameters. So suppose dB is twice the diameter of dA. This ratio will be 2, so this will be a factor of 8. But if you look at the head, it will be a factor of 4 because you have here, and the speed is the same, let us say. Okay. You have square. But this general relation, the first one here is obtained by equating CQ, second one by equating H, and the third one by equating Cp. So when conditions are dynamically similar, you can have two turbines, and if you know quantities for one turbine, and you're given the speed of the other turbine, and you know what is the diameter of the impeller of the other turbine, you can find or predict the Q, H, as well as P. And if you look at the same turbine or identical turbines, then this ratio of length scales is 1. So you have what are called affinity laws, that if T is fixed, as in the case of a same turbine or an identical turbine, then Q is directly proportional to omega, H is directly proportional to the square of omega, and P is directly proportional to the cube of omega when the conditions are dynamically similar, which means that if one of the non-dimensional coefficients is the same. Now, if I look at these two, it means that Q is proportional to square root of H. And if you look at the first one and the third one, middle one and this one, okay, you see that Q is proportional to for other quantities. So here the relation is given in terms of the speed. But this is of course for the same turbine or identical turbines. Now we have already looked at impulse turbines. So in the case of Pelton turbine, you have seen a nozzle producing a high-speed jet of liquid which strikes one or two blades or maybe three blades. Now in the case of a reaction turbine, the working fluid will completely fill all the passages in the runner. So the runner will have many blades, and the passages between adjacent blades will be full of water. Now since the reaction turbine is always full of water, a reaction turbine can handle a larger quantity of fluid. So flow rates are usually higher. And you see that as the fluid in this case the liquid passes through the runner, its pressure will also change, unlike that of the case of the Pelton turbine. So usually reaction turbines have high flow rates and low heads. And a reaction turbine may be either a radial flow type, an axial flow type, or a mixed flow type. And as I have said just now, Kaplan turbine is an axial flow hydraulic reaction turbine, whereas today we'll look at in detail the Francis turbine. It could be a radial flow or a mixed flow. So we'll look at radial flow turbines. So the Francis turbine is a reaction turbine. So during the energy transfer, there's a drop in the pressure as well as a drop in the velocity. So both energy associated with the pressure and the kinetic energy is converted to useful energy. Now, in the case of a Pelton turbine, the pressure is constant in the runner. Okay, but there is a pressure drop taking place in the nozzle. In the case of a turbine, only part of the total head is converted to velocity head before the fluid enters the turbine. But in the case of the Pelton turbine, the entire available head is converted to velocity head at the exit of the nozzle. And then that high-speed jet of liquid strikes the blades of the turbine. Now, we'll see that the conversion of total head partly to velocity head is achieved in stationary but adjustable guide vanes. So this is a view of a Francis turbine. So this looks similar to the centrifugal pump with a diffuser, but the direction of flow is reverse. So this is the penstock, the vertical pipe through which the water will enter. So the water in this figure will go down, okay, and it will go swirled in this volute or scroll casing. So as the fluid goes along this path, you see the area will decrease, and you have a number of guide vanes. So these red vanes are what I call guide vanes. They're fixed or stationary. However, there is a pivot, and you can change the blade angles. So this is the impeller, and the center circle is the eye of the impeller, which is, so these blue curves represent the blades of the runner, which will rotate. Okay, so the blue blades will rotate and the red blades will remain stationary. Now, I've shown the other view. Okay, so the volute appears in this case, the flow, as you can see, this side and this side are not symmetric because the cross-section area has changed. Okay, and the red lines here indicate the edges of the guide vane. Okay, so in this view, the liquid will enter radially inwards. In the case of the centrifugal pump, the flow is radially outwards. So here it will be radially inwards. Okay, so it will pass through the guide vanes and then enter the vanes of the impeller. Okay, and it will turn and go down axially. So at the exit of the runner, this is not open to the atmosphere because then the efficiency will be lower. Okay, you have a diverging passage, a duct, which is called a draft tube, and this will be immersed in the downstream reservoir, which you call the tail race. So the upstream reservoir, which is at a certain height, is the head race. So water will enter through the penstock from the head race, and eventually it will go down into the tail race. So the shaft is shown here in this figure by these two vertical lines. So the shaft will be rotated by the action of the fluid. So this is named after Francis, an American engineer, and is useful for moderate or medium heads in the range 15 meters to 300 meters. This is the available head. So the pressures are medium pressures compared to the Pelton turbine, but the flow rates are going to be higher. And overall efficiencies for larger machines usually exceed 90%. Now, in some Francis turbines, the fluid enters radially. These are called radial flow turbines, and I've just shown you an example of that. But there are some Francis turbines where the flow enters the runner at some angle between the radial and axial. These are called mixed flow turbines. Now, the earlier designs, we did not have the stationary guide vanes to direct the flow smoothly onto the passages of the impeller, and hence they were inefficient. The first efficient inward flow turbine was built by Francis in 1849, and therefore, in honor of Francis, all radial flow or mixed flow designs are called Francis turbines. Now, most of the turbines have a vertical shaft, as I've shown already, but small Francis turbines may also have a horizontal shaft. And the electric generator might be mounted on top over here. And it will, of course, mounted on this shaft. So when the shaft rotates, power will be generated, electric power will be generated. Now here I've shown you an enlarged view of the volute casing and the guide vanes, and the central dots are the pivots. And here I've shown clearly the direction of rotation of the impeller is anti-clockwise. So the fluid will enter vertically downwards and move in the anti-clockwise direction, and it will go through the passages between the guide vanes, and it will be directed onto the impeller blades. So these guide vanes are stationary, but the impeller blades will be rotating. And this, of course, is the shaft, and this cross is the center line. Now this is the other view. I've shown it in a bigger view. Okay, so these are the guide vanes in red, and these are the runner blades in blue. Okay, and the green arrow is the direction of the flow. So the fluid will enter radially this way and this way. Okay, and it will turn and go out axially, downwards, and then into the tail race. So as you can see, a radial flow Francis turbine is somewhat similar to a centrifugal pump with a diffuser. Only thing, the flow direction is reversed. So the fluid enters the impeller at the large diameter section and discharges to the eye of the impeller after giving up most of its energy. And the fluid from the penstock will first enter the volute casing or scroll case, which completely surrounds the runner. And as I've shown you already, the cross-sectional area of the runner, the volute decreases along the flow path. Now what the volute does is, it distributes the water to a series of stationary but adjustable guide vanes, which these are also called wicket gates. So you may be given problems involving a Francis turbine where either the phrase guide vane will be used or the phrase wicket gate will be used. They mean the same thing. So these are stationary blades, but adjustable because there are pivots and they can be moved to change the blade angle. So what the wicket guide vanes do is they impart velocity which has a tangential component and also a radial component, and it is radially inwards. And the guide vanes will direct the fluid onto the runner at an angle appropriate to the design. Now, if the angle is not correct, then the efficiency will reduce. So these things will quantify later. The runner consists of numerous closely spaced vanes. So as the fluid traverses the runner, it is deflected by the runner blades. And what happens, as you can see in this figure, the radial component of the velocity is reduced and is gradually changed into an axial component. So at the entry to the runner, you don't have an axial component of velocity. You just have a VR and a V theta, a radial velocity and a tangential velocity. But when it goes out of the runner, it does not have any radial velocity. The radial velocity is 0, but it has acquired an axial velocity. And of course, it may have some swirl also. Although for maximum power, you want the swirl to be 0. So at the outlet of the runner, you have a V theta and a Vz. At the inlet to the runner, you have a Vr and a V theta. This is the radial flow transistor turbine. So we want to reduce the tangential component of the velocity as the fluid moves from the inlet of the runner to the outlet. That is, as it moves inwards, so that there is a change in momentum. Now, from the center of the runner, the fluid is turned into the axial direction and it flows to waste through this diverging passage or tube, which acts like a diffuser and is called a draft tube. Now, if you have larger turbines, you may also have what are called stay rings outside the ring of guide vanes, which act as columns which help to support the weight of the electric generator, which is usually mounted above the turbine. And the stay vanes are so shaped as to conform to the streamlines approaching the guide vanes. But this, of course, is not there in the smaller turbines. Now, here I have shown you a figure. This blue curve represents a runner blade, which is rotating in the anti-clockwise direction about this center line, which is indicated by the cross. So the fluid is entering this way, it is radially inwards. So R equal to R1 is the inlet, and R equal to R2 is the outlet. And here R1 is larger than R2. Now in the case of the pump, we had used again section 1 to be the radius 1 to be the inlet and the radius 2 to be the outlet. But there R1 was less than R2. Okay. So I kept the notation for inlet and outlet the same. The subscript 1 refers to the inlet, subscript 2 refers to the outlet. So now you can see this is the guide vane, which will guide the fluid onto the runner. So this is stationary. So the absolute velocity V1, the vector at the inlet to the runner, will be tangent to the guide vanes. So this angle, and I've drawn this figure. Is a radial line which is vertical. Okay. So the velocity of at the point on the solid impeller blade at the tip, not tip, at the entrance, it then is going to be horizontal and tangent to this circle. And since it's rotating anti-clockwise, it will the vector U1 will point from right to left. Okay. So if you are running at the design condition, the fluid will be directed in such a way that the velocity W1 relative to this rotor moving coordinate system, rotating coordinate system, will be tangent to the blade here. So this is only at the design condition. So U1 plus W1 is your V1. Okay. But here, this angle alpha 1 between U1 vector and V1 vector is the blade angle for the guide vanes. And there is a pivot about which the guide vane can rotate, so alpha 1 can be changed while the turbine is running. And I followed the same notation. The angle between W1 and minus U1 is what we are calling beta 1. Okay. And this angle, which is 180 minus beta 1, I'm calling beta 1 tilde. So this is a case where if you look at the tangential component of the velocity Vt1, it is larger than U1. And the radial component, sometimes also called the flow velocity component or the normal velocity component, is radial inwards. So this is V1 sine alpha and Vt1 is V1 cos alpha, where V1 is the speed of the fluid which is entering the impeller. Now first let us look at the guide vanes or wicket gates. So as I've already mentioned, the wicket gates impart a tangential and a radial velocity to the runner. And the function of the guide vane is to direct the fluid onto the runner at an angle appropriate to the design. And these are adjustable so that the quantity of the flow and the direction of the fluid flow can be controlled. So if you look at this view, okay, the passage when you rotate the guide vanes, not only does the blade angle change, but the area of the passage between two adjacent guide vanes, that also changes. So therefore, we can adjust both the angle as well as the area, and hence the flow rate as well as the direction. So each vane is pivoted, and there is a suitable mechanism such that all of them can be turned simultaneously in synchronism so as to alter the flow rate through the machine and hence the output power. So this we'll talk about later, but there is something called a shifting ring to which the wicket gates are attached, and if you move the shifting ring, then all the wicket gates will move simultaneously, and the blade angle will change, and the opening will also change. So these inlet guide vanes are actually controlled through a mechanism or linkage, which is connected to a servo mechanism, and through that to a governor. So the governor will maintain a constant angular speed of rotation, and the movement of the guide vane will alter the inlet area and the entry angle simultaneously. So the fluid that leaves the guide vane is at an angle alpha 1, and the speed will be v1. So it will enter the runner with an acquired tangential momentum because it has a tangential velocity component. So here I've shown a cut view of the previous diagram. Okay, just showing the angle here. So if you draw the tangent to the guide vanes at the impeller inlet, that is at r equal to r1, okay, and look at its angle with the tangential direction, and that means you have to look at the angle between the vector v1 and the vector u1. This is what you call the guide vane angle alpha 1, and the guide vane angle controls the tangential velocity component, which is v1 cos alpha 1. Now the passages between adjacent guide vanes will be contracting passages, so the area will decrease in the direction of the flow, which means that the velocity will increase at the expense of pressure. So from Bernoulli's principle, you can figure out that the pressure will be reduced and the velocity and hence the kinetic energy will increase as the fluid passes through the stationary guide vanes. So the magnitude of the relative velocity of the fluid relative to the rotor increases from the inlet of the runner to the outlet. Now, in the space between, there will be some small space between the wicket gates and the runner. In this space, there is no torque on the fluid. So as we argued last time, the angular momentum will be constant. So R times Vt will be constant in this space. But there is also, so this is like a free vortex or an irrotational line vortex with an added radial velocity component. So if you have infinite number of guide vanes, as in the ideal case, then the flow will resemble that of a superposition of a free vortex and a line sink, because the radial velocity is negative. Now the runner consists of numerous closely spaced vanes, and a large transit turbine may have 16 or even more than 16 runner blades. So the incoming flow through the guide vanes onto the runner is radial with a significant tangential component, but no axial component. Now when the turbine is running at the design condition, the velocity relative to the rotor is tangent to the blades of the runner. So this blue curve here is the blade of the runner. This is the inlet to the runner. So W1, the relative velocity at R equal to R1 will be such that this angle beta 1 is 180 minus the blade angle R1. Of course, when it is running in off design condition, the W1 vector may not be as shown in this figure. So the guide vanes are designed to give separation free flow. Now we'll see how to control alpha later on. So as the fluid traverses the runner, it is deflected and the radial component is changed into an axial component. And simultaneously, the tangential component is reduced so that there is a change in the momentum, the angular momentum. So if I look at the conditions at the outlet of the impeller at R equal to R2, okay, you see that VT2 will be small compared to VT1, which is at the inlet. So ideally here, the fluid will leave the impeller in a direction which is determined by the outlet blade angle, which is now beta 2. Okay. And given angular speed omega, the magnitude Q2, which is R2 omega, will be fixed. Okay. And accordingly, you will have V2 going this way. So this angle alpha 2 between V2 vector and U2 vector is indicated in this diagram. And this angle beta 2 is the angle between minus U2 and W2. And this angle beta 2 tilde is 180 degree minus beta 2. Now I will show you that you will have the maximum efficiency when alpha 2 is 90 degree. In that case, VT2 will be 0. So the fluid will have angular momentum at the inlet, but no angular momentum at the outlet. So the change in angular momentum will be the maximum. So if you look at the energy transfer from the fluid to the rotor, this is given by Euler's equation of turbo machinery, and I've shown you here the control volume used to derive that. So now one is the inlet, this circle which is at a larger radius. Okay, and this green vanes are the stationary guide vanes. And the outlet of the impeller is at the smaller radius, R equal to R2. So U1 into VT1 minus U2 into VT2 gives you the energy transfer. So here U1 is R1 omega and U2 is R2 omega. Since omega is the same and R1 is greater than R2, your U1 will be larger than U2. And VT1 I can write as V1 cos alpha 1 and VT2 as V2 cos alpha 2. So we are subtracting some quantity here from this product of U1 and VT1. So you'll have the maximum energy transfer when VT2 is 0. That is alpha 2 is 90. So this is an important point to keep in mind. Now I can apply Bernoulli's equation in the rotating frame because the flow will be stationary in a frame of reference, rotating with the angular velocity of the impeller or runner. So this, as you can see, has the relative velocity, relative kinetic energy, the gravitational potential energy, and this term, centrifugal term here. But the energy transfer is the head that is extracted. So the reduction in head from 1 and 2. So head is the sum of pressure and the absolute kinetic energy and the potential energy. So sum of these three quantities at the inlet to the impeller minus the same quantities at the outlet is your energy transfer. Now we have an expression for involving P1 and G dot R1 over here. If we substitute this over here, omega. Okay, so it's a simple exercise. We have already seen this before. Energy transfer has three components. Reduction in the absolute kinetic energy, a reduction in the kinetic energy. This also looks like a kinetic energy, but it is the U1 at the inlet to the impeller and U2 at velocity at the outlet to the impeller. So these are velocities at points on the solid blades, not the fluid velocity. And from that you have to subtract this difference, the reduction in the relative kinetic energy. So the first term is a decrease in the kinetic energy, absolute kinetic energy. The drop in the piezometric pressure as the fluid flows from inlet to outlet. So the pressure of the fluid will change in the runner also, or in the impeller passages, the passage between adjacent blades of the runner. And when the pressure drops, you will be able to extract more energy than in the case of a impulse turbine. And a quantity called degree of reaction is sometimes defined. It is the ratio of the energy transfer by changing the static pressure to the total energy transfer. Now the change in gravitational potential energy can be neglected. So the last two terms actually represents the change in the pressure. That is the amount by which the contribution to E from the change in pressure. And to the numerator here, if I add this quantity, the change in the absolute kinetic energy, then you get E over here. So that is the degree of reaction. Now, the first term here will be positive if V2 is less than V1. That is, you want the fluid absolute kinetic energy to reduce. So the velocity of the fluid, the absolute velocity of the fluid at the exit of the runner should be less. Then this term will be positive. Now, middle term is always positive because the fluid is moving radially inwards. Okay. And if you look at the last term, here I have written it in the form of plus W2 square minus W1 square, or here it is minus of this. Okay. So you see that you must choose the design such that the area of the passages between adjacent runner blades decreases in cross-sectional area. So you want W2 to be actually larger than W1. So if W2 is larger than W1, okay, this term will be positive, but if you look at it here, this term, you have a minus sign here, and this will be negative if W2 is larger than W1. So in a well-designed transistor turbine, all the three terms shown above will be positive. So we have them. But now if you look at it this way, when will you have the maximum E? When V2 is minimum. Because you're subtracting V2 square, a positive number, from V1 square. Okay. These two are determined by the geometry and the angular speed. And this is determined by the area between the passages. Now V2 square I can write as VR2 square plus VT2 square. Because it's now, but VR2 depends only on the flow rate and the geometry. So for a given flow rate, this VR is constant. So VT2 will be minimum when V2 will be minimum when VT is minimum. And you want V2 to be 0. V2 cannot be 0 actually, but VT2 can be 0. So when VT2 is 0, you will have the minimum V2 because for a given Q. For a given flow rate, this first term on the right hand side here is constant. And since this is non-negative, okay, only when it is 0, you will have a V2 at this lowest. So when will VT2 be 0? Well, if you go back and look at that figure, the tangential component will be 0 when VT2 absolute velocity is radial at the outlet. Here, radial in this view, okay. But if you look at the draft tube, there it will be axial. So whatever it is, the angle must be 90 degree. So that VT2 is 0, and that will give you the minimum value of V2 for a given omega. That means for a given value of the speed U2. So the vanes of the runner are designed or possible no wall component or swirl component so that V2 is minimum. So as a design condition, VT2 must be 0. So this is accomplished by reducing the inner diameter and having the vanes turn the flow so that it leaves the runner with a velocity that is largely axial. So at the exit of the runner, you will have an axial component as well as a VT component, the tangential component. There will be no radial component. But you want the tangential component to be as small as possible so that the magnitude of the exit velocity is small as possible. So the power that you're extracting from the fluid, okay, when the runner is rotating will be the mass flow rate rho q multiplied by this difference. Product of u times Vt at 1 and u times Vt at 2. So at the design condition alpha 2 is 90. So at the design point, the energy transfer is simply u1 Vt1, which is u1 V1 into cos alpha 1. So design point will be the point where the blade angle for the blades. So the power at the best efficiency point will be rho q u1 v1 times alpha 1. But this alpha 1 at the best efficiency point will be related to beta 1. And if you want to look at the hydraulic efficiency, it is the power that you're extracting divided by the power that is available. So at the design point, when alpha 2 is 90, it is simply u1 v1 cos alpha 1 by gh. And if you want to look at the inlet normal velocity from this view, okay, it will be controlled by Vn1 or Vr1, which is V1 sine alpha 1. And this Vn, you know, is Q flow rate by 2 pi R1 V1. So the volume flow rate, if you wish, you can express in terms of V1 and alpha 1 as Q equal to 2 pi R1 V1 multiplied by V1 sine alpha 1. So this might be useful for solving problems. So I've given you all the relevant equations. Now the pressure at the runner exit usually will be below atmospheric pressure. And from the center of the runner, the fluid will go into the draft tube in the axial direction. So I've shown a small view here showing the draft tube. The lower end of the draft tube must, under all conditions, be submerged below the level of water in the downstream reservoir or tail race, so that the turbine is always full of water. If the level of water in the downstream reservoir falls below the level of the draft tube, then some air might enter, and that is what you want to avoid. That is, you don't want the liquid which is coming out of the turbine to exit to the atmosphere directly. It should exit underwater in the. So a carefully designed draft tube will reduce the velocity of the discharged water so that the kinetic energy that is lost at the outlet is minimized. So the kinetic energy of the fluid at the outlet of this draft tube is simply not useful. It is, you can say, the available energy is lost. So the draft tube acts in such a way as to reduce the pressure at its upstream end to a value less than atmospheric pressure, so that the pressure drop across the runner is as large as possible, and hence the energy transfer is as large as possible. Now, we have looked at governing of Pelton turbines. So let us look at governing of Francis turbines. So as in the case of the Pelton turbine, the speed must be kept constant, otherwise the line frequency of the electrical output will change. So here you will have a governor which will actuate a mechanism that they will regulate the gate openings, the wicket gate openings, and the guide vane angles. And usually a relief valve or surge tank is put so that when you change the vane angles, the pressures generated by the water hammer effect is not too large. Now an invert flow turbine is to some extent what is called self-governing, because there is a centrifugal head which in part balances the supply head, which is the gravitational head. Now we'll look at a relation between the guide weight angle, the volume flow rate, and the rate of rotation. So we'll assume that the turbine is running at the best efficiency point, so there is perfect guidance of the liquid onto the guide vanes. So this is what is called shockless entry. So under that condition, see the relative velocity vector is tangent to the blade. Okay. Now, if you look at this inlet velocity triangle, the tangential component here, the ratio of this to the radial velocity or Vn1 is your cot of alpha 1. Okay. So Vt1 I can express in terms of the flow velocity and cot alpha 1, and this will depend on the flow rate. Also, if you look at this big triangle, your Vt1 is U1 plus this small quantity here, which I can express in terms of cot of beta 1 tilde. So if you look at the same flow velocity Vn1 and take not cot of alpha 1, not cot of this angle, but cot of beta 1, you'll get this value, this small length over here. To that, if you add U1, you get again Vt1. So if we equate equations 5 and 2, we have a relation between alpha 1 and beta 1 tilde, which is 180 minus beta 1 or pi minus beta 1. So you have this relation that cot of alpha 1 is U1. If I look at this equation, this equation on the left and the middle equation here is equal to Vt1, which also you can write as V1 cos alpha 1. But if I look at this equation here, first two, okay, I can divide by Vn1. Then I have cot alpha equal to this ratio U1 by Vr1 plus cot of beta 1 tilde. So at the design condition, you have got a relation between beta 1 tilde and alpha 1. Now beta 1 tilde is fixed because that is dependent on the blade angle. But alpha 1 can be altered because the guide vane has a pivot, and you can rotate the guide vane about the pivot to change alpha 1. Now what is U1? Well, U1 is simply R1 omega, and Vr1 I can express in terms of the flow rate and the geometric parameters. So you have cot alpha 1, a relation between alpha 1 and beta 1 tilde, which involves omega and Q. Now as you can see, for a given turbine, once it has been designed and manufactured, beta 1 and hence beta 1 tilde will be fixed, R1 will be fixed, P1 will be fixed. So what can be varied is omega and Q and alpha. So there is a relation between alpha 1, Q and omega, which I can write in this form, some functional form equal to 0, and I put a semicolon and written the constant parameters, which depend on the design of the turbine. Okay. So this relations in either one of these forms, 12A, 12B, and 12C are all equivalent forms. These are the conditions for shockless entry. Now the angular speed must be kept constant so that the frequency of the electrical output is constant. So if you want omega to be fixed over here, whenever you change Q, you have to change alpha 1 because beta 1 is fixed. Otherwise, the turbine will not run at the design condition, which means that this relative velocity vector will not be tangent to the impeller blades, and there will be shock loss, which we have discussed in the context of a centrifugal pump. So this is called, the condition represented by those three equations is called shockless flow. So it tells you how to change alpha 1 with changes in flow rate such that omega is constant. And this will enable you to have a situation where the relative velocity vector W1 at the inlet is tangent to the blades. Now, what is the purpose of the movement of the guide vanes? You can see here, the power developed by the turbine is the efficiency into rho g times the available head into the flow rate. Now, the available head is a constant, but the power will change according to the electrical power demand. So this is the power that at steady state, the power developed by the turbine will be equal to the power demand, electrical load. So if P changes, then what will happen? And H is the same. Q must change because you want eta to be the same. Eta must be at its maximum value. So therefore, the volume flow rate has to be changed in such a way that the turbine operates at its best operating point. So that means you must change both alpha as well as Q simultaneously when the power changes. So when the power changes, Q must be changed so that the efficiency is maximum. So, but to keep the efficiency maximum, you have to change the alpha 1. So Q and alpha 1 both must change. So if I go back and look at this relation again, this gives you a hint. So when the power changes, you have to change Q1. But you want to keep omega constant. So therefore, if omega is to be kept constant and Q is changed according to the power demand, you must change alpha 1. So alpha 1 and Q have to be changed simultaneously because beta 1 and hence beta 1 tilde is a constant. Alright, now let us look at the draft tube. As I said before, the draft tube must be properly submerged. So you have a submerged discharge. And the water after passing through
Sir, you have been muted.
So I'm stopping the recording.